Last time we were learning to identify aromatic versus anti-aromatic molecules. Remember, it needs to be cyclic, planar, fully conjugated, and it needs to have the right number of pi electrons, which we've said is 2, 6, 10, and so on. If it has an odd number, if it has 4, 8, or 12 pi electrons, it's anti-aromatic. And we'll give you some examples of both of those as we continue on. I think at the very end we were talking about how to deal with lone pairs on heteroatoms, and the conclusion is they only count if they're in a p orbital. How can you tell whether the lone pairs are in a p orbital? Well, you look at what the nitrogen is involved in. If it's already, and you estimate its hybridization, this nitrogen is already participating in a double bond, which means the lone pairs on that nitrogen can't be in a p orbital. They have to be in an sp2 orbital. sp2 orbitals are orthogonal or perpendicular to p orbitals. That is, they're not participating in the pi system. They don't count as part of the pi system, and so only those highlighted in pink count, and this is aromatic. This one called imidazole is tricky. It's got two different nitrogens with two lone pairs, one on each nitrogen, and one of them counts and the other doesn't. So this lone pair doesn't count because, like the nitrogen in the six-membered ring that we just looked at, that nitrogen is sp2 hybridized. You can account for the sp2 orbitals in these two carbon-nitrogen bonds, and in the lone pair, the p orbital on the nitrogen is involved in this pi bond. So the lone pair can only be in an sp2 orbital. That means it's, again, perpendicular to or orthogonal to the pi system in the ring. That means it doesn't count. This lone pair, some of you looked at that nitrogen and you thought that thing is sp3 hybridized. And that's a sensible conclusion, but it's wrong. The reason it made sense to you is because you've gotten used to looking at atoms and saying, okay, how many groups are they surrounded by? If it's 4, it has to be sp3 hybridized. That's usually true except for when a lone pair is adjacent to a pi bond. When a lone pair is adjacent to or next door to a pi bond, it will be in a p orbital so that it can participate in resonance stabilization. So these lone pairs, this nitrogen is in fact sp2 hybridized. The lone pair is in a p orbital. It does count, and there's 2, 4, 6 pi electrons, and so this molecule's aromatic. Okay, follow-up questions on how to deal with lone pairs on nitrogens. Okay, let's go again with another one. And let's do let's do an aromatic molecule. Let's do molecules that could be aromatic or anti-aromatic that have multiple rings in them. It turns out that these multiple ring systems follow the same rules as a simple, smaller individual ring. That is, if it's cyclic and fully conjugated and has the right number of pi electrons, it can be aromatic. So what do you conclude about this one? 2, 4, 6, 8, 10. 10 pi electrons, that satisfies the 4n plus 2 rule. So yeah, indeed, this is aromatic. That molecule is called naphthalene. How about this one? Let's deal with the nitrogen first. Do the lone pairs count? Does a lone pair count or not? Yes, you can tell because it's adjacent to a pi bond, so it's in a p orbital. So 2, 4, 6, 8, 10, again, aromatic. Good. Except we can't spell. Here's one that's in your text. What do we do with oxygens? Oxygens have multiple lone pairs. We're going to follow the same considerations with oxygens as we did with nitrogens. Lone pairs in a p orbital count. Those that aren't, don't. Now, again, if you looked at an oxygen, you could be forgiven for thinking that that oxygen was sp3 hybridized because it's surrounded by 4 groups. But remember that when a lone pair is adjacent to a pi bond, the lone pair is going to be in a p orbital so that it can participate in resonance. So we would count these 2 and 1 lone pair each on the oxygens. Okay? And we would say that the molecule is anti-aromatic. Now, yes, go ahead.
Was there just a particular reason why we only counted 1 lone pair on the oxygen?
We only count 1 lone pair on each oxygen because if 1 lone pair is going to be in a p orbital so that it can participate in resonance, that means the oxygen's sp2 hybridized. That means this bond comes from an sp2 orbital on oxygen, so does this bond. The other lone pair has to be in an sp2 orbital. So maximum of 1 lone pair on an atom can be in a p orbital participating in the pi system. Yep. Yes? It's anti because of the 4n rule. Yeah, you have 8 pi electrons, that's the 4n rule. Okay. Now, here's a nuance that I told you last time to put an asterisk in your mind by the phrase anti-aromatic. And I want to illustrate something that tends to happen with molecules that are anti-aromatic. We'll figure out how to deal with it, and I'll tell you exactly what I want you to be able to do. And that is to look at something like this and predict that it would be anti-aromatic. What your text says, and this is actually true, is that because anti-aromaticity is so destabilizing, molecules will sometimes distort their geometries to avoid being anti-aromatic. Recall that for a molecule like this, the MO picture for the molecule has 1 lower energy orbital than pairs of degenerate orbitals like this. If we have 8 pi electrons, I'm just adapting the orbitals for benzene because we have 1, 2, 3, 4, 5, 6 p orbitals on each of these atoms, which we're going to mix to make the 6 pi molecular orbitals. If I filled these with 8 electrons, 2, 4, 6, 8, you can tell how bad this is because I essentially have 2 electrons unpaired, it's a diradical, and they're in an antibonding orbital. So that's kind of bad. Those electrons are higher in energy than they would be if the molecule weren't anti-aromatic. And so in some cases, what the molecule will do is distort its geometry so that it no longer satisfies all the criteria for being aromatic. That is, remember, to be either aromatic or anti-aromatic, you have to be cyclic and fully conjugated and planar. So one of the most common things that anti-aromatic molecules will do is distort themselves from planarity so that they don't have to be anti-aromatic. For example, this molecule will form sort of a boat shape. Do you see how the 2 oxygens have puckered themselves out of planarity? That non-planarity breaks conjugation and destroys anti-aromaticity. So in reality, what I'm telling you is those oxygens probably, rather than being sp2 hybridized, they probably rehybridize as sp3 so that they can avoid anti-aromaticity. Now that's kind of a convoluted story, isn't it? Because in reality, the real structure of this molecule that I've drawn is probably just not aromatic and not anti-aromatic. But the reason that it's distorted from planarity is because it's trying to avoid anti-aromaticity. So when you see this structure, I want you to know that if it were cyclic, if it were planar and fully conjugated, it would be anti-aromatic. When you see this structure, you're going to answer that's anti-aromatic. And then you're going to know that one consequence of anti-aromaticity is often that the molecule is going to distort its shape so it doesn't have to be anti-aromatic. Does that make sense? Usually, so, and this is where your text gets a little bit funny. They're not wrong, but it's a little bit confusing. In questions that I might give you, if I want you to conclude that something's not aromatic, I'll do something like that. Right? Why isn't that aromatic? It's not fully conjugated, right? So it's just flat out not aromatic. Or something like this, right? Not cyclic, therefore not aromatic. So the reason we're going through this is because when you do some of the practice problems in the study guide on the problem set, you're going to look at something like this, and this is one of the problems, and then you're going to look up the answer, and it's going to tell you that's not aromatic. And it should have said anti-aromatic. Now, the text is right. By the time it distorts its geometry, it is no longer aromatic or anti-aromatic, it's just not aromatic. But the whole reason it's not planar is because it's trying to avoid anti-aromaticity. Does that make sense? Okay, so yes, go ahead.
Anti-aromatic molecules do that, like where they distort their.
Many of them do, or they will be so reactive that they're very hard to isolate. As an example, cyclobutadiene, you can't really observe except at 4 Kelvin, like really, really, really cold. And even then, cyclobutadiene tries to increase the length of these sigma bonds to pull those pi bonds a little bit out of conjugation. So yeah, distortions of geometry are really common for anti-aromatic compounds. And you'll see this. But what I want you to do is to be able to detect when a molecule would be anti-aromatic. Yeah, go ahead.
Is not being anti-aromatic energetically favorable? Is that like what's the reasoning behind that?
Yeah, is not being anti-aromatic energetically favorable? And the answer is yes. So let me show you the orbital picture for cyclobutadiene. Here are the 4 pi molecular orbitals for cyclobutadiene. If it were completely planar and anti-aromatic, that's the picture you get, a diradical. If it distorts its geometry a little bit, you end up with, you break the degeneracy between the orbitals, you end up with this picture, and it looks like that. So the electrons are able to move down in energy a little bit. And that's true for all of these distortions. They allow the high energy unpaired electrons to move down in energy and to no longer be unpaired. Yeah?
Sorry, can you go back to the one, the double oxygen?
Yeah.
And just explain the conjugation of that. Well, how is that fully conjugated? Just because the electrons on the oxygen?
Right. So imagine each of these oxygens is sp2 hybridized.
Yes.
That would mean one lone pair is in an sp2 orbital, the other's in a p orbital. Fully conjugated means I have p orbitals on each and every atom in the ring, and they can all line up with each other. Yep.
Thank you.
Yep. What else? Okay. You can use the concept of aromaticity to answer interesting questions. For example, I'm going to draw two hydrocarbons. And that one kind of looks friendly. Been told my 7-membered rings look like robots. But anyway, I could ask, one way of asking a question is which of these protons is more acidic? Okay, and that question on the surface doesn't appear to even have anything to do with aromaticity, but it actually is about aromaticity. And the way you're going to come to that conclusion is to say, okay, well, if I don't know what to do in a question about acidity, I always draw the conjugate base. So go ahead and draw the conjugate bases of those two molecules. That is, what would be left behind when we remove a proton. Oh, now the 7-member ring looks sad. Still looks sad. Well, whatever. Okay, so which of those, the question, which of these is more acidic, is the same question as which of these is most stable. So, what do you conclude? Which of these is most stable? One on the left. Okay, that's right. How do you know that? It's aromatic because it keeps the 4n plus 2 rule, right? Whereas this one, oops, I don't know why we turned into an eraser there. This one is least stable because it is anti-aromatic, which is why it looks sad, actually. It's sad because it's anti-aromatic. Oh, all right. So that would mean that this proton is more acidic. Follow the reasoning? Yeah.
So this one on the left has 6 pi electrons? Is that how?
Yep. Yep, the one on the left has 6 electrons in the pi system. This one has 8. Yeah?
Do you happen to know the pKa of that?
I don't, not off the top of my head. It's a good question. I know that the corresponding anion is actually pretty stable and is involved in various organometallic complexes. It's called the cyclopentadienyl anion. So the pKa is pretty low, but I don't exactly know what it is. Okay. You could ask this question in other ways too. For example, what if we put a leaving group instead of a hydrogen? And then what if I said, which reacts fastest in an SN1 reaction? And again, you on the surface, you're going to be like, oh, SN1, that's 351 stuff. Why the heck is he asking us about that now? And the answer is because I'm evil, but also because it applies to what you're learning. It's actually a question about aromaticity. What's the first step in an SN1 reaction? Well, the leaving group leaves. So this is really a question, and that steps uphill, and it's more uphill for carbocation intermediates that are more unstable. So this is really a question about which carbocation intermediate is more stable. The one that's more stable should, the reaction that leads to it should go faster. And here I'm running out of space, so there we go. So draw the carbocation, which I've now made happy to disclose what the answer is, but it's obvious at this point, right? 6 electrons, 4 electrons, aromatic, anti-aromatic, faster in SN1 because this is a more stable carbocation. Okay, yes?
Is it fully conjugated?
Yes, with the positive charge on that carbon, you would conclude that this carbon is sp2 hybridized with all of the carbon, and carbon-hydrogen bonds coming from those sp2 orbitals. The positive charge is associated with a p orbital on this carbon.
So it's just empty, but there is a p orbital
Yep.
in line with everything else.
Yep, empty but in line with everything else, and then once you line them up, you've got 6 electrons total. Yep. All right, others? Okay, there's one more thing that I've sort of alluded to. There have been a couple of times today and last time when I drew the orbital picture for a simple hydrocarbon. I did it for benzene or for this 6-membered ring here. I did it for an 8-membered ring last time. You'll notice a characteristic pattern. Again, this comes from the MO picture. There's one low energy orbital, and then there's pairs of degenerate orbitals all the way up until you either get to the number of atoms in the ring anyway, there's as many pi orbitals as there are p orbitals that you start with. If you have an even number of atoms in the ring, even number of p orbitals, there'll be one that's lowest, one that's highest, and pairs of degenerate orbitals. If you happen to have, as is the case for a 5-membered ring, an odd number of atoms in the ring, there will always be one that's lower in energy, and then there will be pairs of degenerate orbitals all the way up. So this is a consequence of the math of MO theory. If you forget it, there's a pretty simple mnemonic device you can use. It's in the text. I don't want to spend more than a couple of minutes on it. It's called the Frost circle, or the inscribed polygon method. And basically, it's kind of neat because you draw a circle. Let's see. You don't actually need to draw the circle, but you draw a circle, and then you draw the shape of the ring. And it needs to be like a perfect polygon. So if you were going to draw a square, you draw a perfect square. If it was a 5-membered ring, you'd draw a perfect pentagon. And I'm not sure I can do that, so let's just try. That's not perfect, but it's close-ish. Okay. The idea is that you take your 5-membered ring and you draw a 5-membered ring, you inscribe it on the circle. And again, I'm looking at that, all the lengths of that pentagon are not identical. If they were, if I could get it to be that way, where the polygon touches the circle is the energy level for the molecular orbital. And the nice thing about this mnemonic device is it's absolutely quantitative if you draw your polygon right. What I mean by that is if you take the halfway point through the circle, sort of draw the diameter across the middle of the circle, this is the dividing line between bonding orbitals and anti-bonding orbitals. So this is a nice way. We went through that analysis last time talking about like counting bonding interactions versus anti-bonding interactions. This method will give you exactly the same answer. So we now have, and it actually works out to scale. Like you can do the math and figure out the energy levels of the orbital, and this distance in space between this line here and these lines here is quantitative. It's pretty close to what the number actually is when you measure it. But for example, for the cyclopentadienyl cation, we can do this now and show that even though it looks like there's a lone pair on that atom, all 6 electrons are actually in bonding orbitals. And that's why it's a stable anion, that's why it's aromatic. Of course, these 2 anti-bonding orbitals will be empty. Once you get used to this, you don't even need to do the polygon anymore. If you recognize the pattern that I just showed you, for example, this picture for the molecular orbitals in this 8-membered ring, you can get from the polygon method, you inscribe the 8-membered ring, the stop sign on a circle with 1 point down, and then every other place that 8-membered ring intersects the circle is a place where there's an orbital. So there's some problems in the text that will allow you to reason your way through this. It's a useful mnemonic device when you're first getting started thinking about why things are aromatic versus not. Okay, are there any questions about that? All right. Well, that sort of concludes chapter 19. I hadn't intended to get to chapter 20 this quick, and some of you may not be ready to move on to that at this stage, but you got an exam that opens Monday, and we want to be done with chapter 20 by then. So we're going to go ahead and get started. What I want to give you is an overview on chapter 20 that will help you see what all of the new reactions, what the new reactions we talk about have in common. So what we've done so far is simply background. You need to understand that aromatic molecules are very stable. I told you last time that aromatic molecules don't react like alkenes, right? Told you, for example, if you take an alkene and you add bromine as an electrophile, you do an addition reaction and you get the 1,2 vicinal dibromide, and this is an addition product. And in that addition product, the pi bond is gone, right? And in fact, you've lost the carbon-carbon pi bond and the bromine-bromine sigma bond. It turns out that if you take bromine and the benzene ring, you get no reaction, because the benzene ring is aromatic, and if you imagine what would happen if we tried to do with one of the pi bonds of the benzene ring what we did previously with the alkene, that would be no longer aromatic, right? Because it's no longer conjugated. So benzene doesn't want to do the addition chemistry that alkenes do, because doing so destroys aromaticity. Now it turns out that you can get benzene to react as a nucleophile. Benzene can be a nucleophile, but you need a very reactive electrophile. So one strategy, whenever you want to soup up an electrophile, make an electrophile that you already have even better, is to add a metal to the reaction, a metal ion, a metal cation that can act as a Lewis acid. Remember that a Lewis acid is simply an atom that has an empty orbital that can accept electrons into it. So an example of that would be to take bromine and the Lewis acid iron tribromide. Now, you don't need to know anything about iron as a transition metal other than iron tribromide has an empty orbital, a low energy empty orbital that can accept electrons. In other words, it's a Lewis acid. And it turns out what happens when you bring iron and tribromide and Br2 together is that one of the lone pairs on the bromine will actually attack the empty orbital on iron, and that will generate the following intermediate. which we will draw like this. It's got a negative formal charge on iron and a positive formal charge on bromine. Now you're used to looking at, in 351, you were used to looking at bromine as being a good electrophile, because if a nucleophile attacks the one bromine on the end, the other bromine, Br minus, is a good leaving group, right? You've already said before, Br minus was a great leaving group. Its conjugate acid is HBr, its pKa is something like -9. Super good leaving group. Not good enough for benzene. When you add the iron to the bromine, what is over here is an even better leaving group. This is a super leaving group. And this molecule overall is a super electrophile, meaning it's more electrophilic than it would be without the Lewis acid of iron tribromide. Okay, so what can you expect benzene to do in the presence of that super electrophile? Well, now that the electrophile is reactive enough, the pi electrons in benzene are now high enough in energy relative to the electrophile to do the attacking. So we take pi electrons from benzene. We're drawing it as though they're coming from one of those double bonds. In reality, you know the MO picture for benzene. You have two degenerate pairs of electrons in the highest energy orbital. And they're delocalized over the whole ring. It's one of these two, pi 2 or pi 3, you can't tell which, and we won't worry about it. You'll just draw the mechanism as choosing one of the bonds in the benzene ring to attack the electrophile. Then you'll have the super good leaving group leave, and then we'll draw that intermediate. Now, in the case of just using benzene as a starting material, one of the carbons is going to get the new electrophile and the other is going to get a positive charge. It isn't going to matter when we're just dealing with benzene because all the carbons are identical. But at a later point, if benzene has additional groups on it, it will matter which carbon gets the electrophile. And we'll deal with that in a second. Probably maybe on Friday. That's called regioselectivity, and we'll deal with that later. But first we need to go through the individual reactions. So for our purposes, let's just say the carbon on the at the top gets the bromine. The other carbon gets a positive charge. Now, in alkene chemistry, in these addition reactions, usually a nucleophile would attack this positive charge and you get an addition product. But as we just barely said, if you do that for benzene, you lose aromaticity, right? If we just had bromine come back in and add to that positive charge, we would lose aromaticity. So instead, what happens is we do an elimination reaction. So this was an addition step. Then we're going to do an elimination reaction. And that should make sense because you have a positive charge and an adjacent hydrogen atom. And that the hydrogen we're going to remove is the one that's on this sp3 hybridized carbon in this no longer aromatic intermediate. Right? This is it's not aromatic, it's a resonance stabilized carbocation. And in fact, the elimination reaction here is super fast because it's super exothermic, it's super downhill, because if we do the elimination reaction, and it doesn't take a very strong base to do this, it's probably Br minus that does this, but we won't even worry about what the base is because it doesn't need to be very strong at all. We'll remove that proton, electrons will kick down and form a pi bond, and then restore aromaticity. And so what we've done, we told you that alkenes with electrophiles do addition reactions. Benzene and aromatic molecules don't do addition reactions. They do overall substitution reactions. There's an addition step, and then there's an elimination step. Overall, watch what this does. We swap out the hydrogen for the bromine. And that reaction series is called electrophilic aromatic substitution, or EAS, electrophilic aromatic substitution, always involving an addition step and then an elimination step to restore aromaticity. And always it's the proton on the carbon where the electrophile just added, it's always that proton that gets removed. Okay? All right, questions about that mechanism? All right. So you can do this not only with bromine, of course, but you can do this with chlorine as well. So if I used Cl2 and FeCl3, I could replace a hydrogen on the benzene ring with a chlorine. The particular reaction that I just showed you, either with Br2 or Cl2, is called aryl halogenation. But this is an example of an electrophilic aromatic substitution reaction. Aryl refers to an aromatic ring. That's an abbreviation. We talked about like alkyl halides, we have an alkyl group on them, acyl chlorides that have an acyl group on them. Now we're talking about aryl halides. That is a halide that has a benzene ring or an aromatic ring attached to it. So there's a whole section in your text about aryl halogenation. It follows this basic mechanism of first you make a superreactive electrophile, then benzene attacks the electrophile, then we restore aromaticity to get the substitution product. Okay, yeah?
Does the iron compound have to match the halogen?
Does the iron compound have to match the halogen? I don't know. I think so because they choose it that way, but there's no explanation in the text as to why it needs to be that way. And there are other Lewis acids you could use besides iron, but that's what's chosen for this particular example. Okay, what else? All right, well, we're going to do more. There's about 5 new basic reactions and then some others beyond that, but sort of 5 new electrophilic aromatic substitution reactions. The next one we're going to talk about is called aryl nitration, and this is going to be attaching a nitro group to a benzene ring. So you will start with, again, a benzene ring. You'll use nitric acid and sulfuric acid. If you've ever dealt with nitric acid and sulfuric acid, these are not friendly neighborhood conditions. You've got to do that in a fume hood. You got to be careful not to get any on you. But when you're done, you have a nitro group on the ring. It may be useful to you at this point to draw the Lewis structure of the nitro group, just so that you remember what it looks like, because its structure is going to become important a little bit later in this chapter. Okay, so, and there are reasons you'd want that nitro group to be there, and I'll illustrate that in just a little bit. But how does the reaction go? it turns out that under the conditions of nitric acid and sulfuric acid, you make some of this electrophile. Now, how that happens is, I don't think, described in detail in your text. If you want to see it, we can talk our way through it just real briefly, but it's not something I'd hold you responsible for. This is nitric acid. It's got a positive formal charge on the nitrogen and a negative formal charge on the oxygen. And then you've got H2SO4. So you've got a very acidic mixture. Certainly this acid, sulfuric acid, could protonate on this negatively charged oxygen, and that happens. But that negatively charged oxygen is resonance stabilized, and it's possible that at least at another point, sulfuric acid might protonate on the other oxygen. When it does, you turn that oxygen into a supergood leaving group, and then the negatively charged oxygen attached to the nitrogen can be a kicker-offer and kick off that leaving group to give you the the NO2 cation. I'm not going to actually hold you responsible for, and I don't think your text actually shows the mechanism for how that electrophile is made. You'll just need to remember that when you have nitric acid and sulfuric acid, you make that NO2 plus cation. Then the benzene ring attacks. And we break a pi bond, kind of like carbonyl chemistry there. Here is the intermediate that we're going to get. One of the carbons has a hydrogen and the new nitro group. The other carbon has a positive charge, and then, so that's the addition step. And then the second step is the elimination step, where a base, probably the conjugate base of sulfuric acid, removes the adjacent proton, electrons kick down, and we restore aromaticity. All right. Questions about nitration? Yeah, go ahead. No?
And is that weak conjugate base just in the solution already from the acids?
That's right. Whatever is doing this is likely the conjugate base of the acid that's already present in solution. Yep. Okay. A couple things about nitro groups just to get you prepared. Nitro groups can be convenient ways to accessing other nitrogen-containing compounds. Here's a reaction that we're not going to, so this is the substitution product. Here's a reaction that we're not going to know the mechanism of. It involves a familiar reagent though. If you use hydrogen and palladium on carbon, that's palladium metal immobilized on charcoal to increase its surface area. You can do a reduction reaction that converts the nitrobenzene converts the nitro group into an amino group. And that's actually pretty useful because there's a lot of things we can do with amino groups. The molecule that has, this is just a sort of non-systematic name for benzene rings that have amino groups on them. The term is aniline. I will use that periodically in the class, so if I say aniline, you'll know what I'm talking about. The reason that you want to sometimes convert the nitro group to an aniline is because the properties of the nitro group are different from the properties of the benzene ring. So to illustrate this, I'm actually going to draw the Lewis structure of the nitro group. And I want you to notice that the atom that's attached to the benzene ring in the nitro group has a positive formal charge on it. And I want you to notice that that atom is attached via a pi bond to an electronegative oxygen. And that means I could use resonance I could draw a resonance structure in which I actually move electron density out of the benzene ring and onto the oxygen of the nitro group. So let's go ahead and draw that resonance structure. Now, it's true that that the benzene ring's aromatic and we don't want to remove all the electrons from the benzene ring. And so you're right, you're correct to say that this nitrogen is, this resonance structure is a minor contributor. Nevertheless, it tells you that one effect of the nitro group is to withdraw electron density from the benzene ring. And in fact, you could draw other resonance structures. I'm going to highlight the positive charge. And I want you to, at some point today or tomorrow, draw the other resonance structures that are possible for this ring where the positive charge is going to end up on those other 3 carbons. Do you see how we get those? We take the electrons in the pi bond, we move them over to the one that has the positive charge. Okay. So we're going to call the nitro group an electron withdrawing group because its effect is that by resonance, it withdraws electron density from the benzene ring. Now, how does the aniline differ? Well, the aniline's got a lone pair on the atom adjacent to the ring. And when that happens, you can draw a resonance structure where you form a new pi bond between the nitrogen with the lone pair and the benzene ring carbon. And then you move the electrons from that carbon-carbon pi bond out onto the adjacent carbon atom to make this resonance structure. And again, you can argue that this resonance structure is a minor contributor, and you're right, but what it tells you is the effect of that aniline nitrogen is to donate electron density into the ring. And again, I won't draw these resonance structures now, but you should do that either sometime today or tomorrow to convince yourself that this negative charge can actually be delocalized in all of the spots I've highlighted in pink. Because of that, we're going to call the aniline or the nitrogen an electron donating group, by which we mean that because of resonance, it is donating electron density to the benzene ring. Whether or not a benzene ring has a withdrawing group on it or a donating group on it is going to have major consequences. And so you need to start thinking about, if a group is on a benzene ring, is it a donating group or a withdrawing group? And the fact that that will have consequences is one reason why this reduction reaction is useful, because with a very simple reaction, you can change something from what used to be a withdrawing group to something that's a donating group. And that'll have some downstream consequences. So as we introduce each of these reactions, we're going to be thinking about, is the group we just installed a donating group or a withdrawing group? The halides are sort of tricky. They have lone pairs on the atoms adjacent to the benzene ring. So the halides are electron donating groups by resonance. But chloro, at least, and to some extent bromine, is an electron withdrawing group because of electronegativity. And we will see with some of these groups there's dual character. They can donate by resonance, but they can withdraw because of electronegativity. And we'll have to sort of have a way to offset those two to decide what the overall impact of that group is going to be. All right, well, more later. We'll see you on Friday. Have a good Wednesday.